Alright, so here comes part 3. We are at problem 7. 7 through 9 represents problems from the polarization, which is section 2410. So you have two polarizers that are oriented 72 degrees to one another. So here's your first polarizer, here's your second polarizer. And this is just a cross section. So unpolarized light comes in, falls onto the first one, and then some light comes out, and you will see in a textbook, you will know that if unpolarized light comes through the first polarizer, the light transmissible to the first one, it's half of the intensity of the original or the first intensity. And the question is, what fraction of the light intensity is transmitted all the way to the end? So essentially they ask you, hey, what is I2 divided by I0 or I0? When the light goes through the second polarizer, what comes out, the transmitted light, is I2 is the previous one, I1 cosine square of theta. Okay, so now we have theta as being 72. So we're going to plug in, so I2 over I0, instead of I2, I'm going to write I1 cosine square of theta, divided by, instead of I0, multiply here with 2 on both sides, and you get 2I1. Simplify I1, and you get nothing else but cosine square of theta over 2. Plug in your theta, which was 72 degrees, make it squared, yeah, don't forget to do that, divide by 2, and you get this number. What does that mean? That means that only about 4.8% of the light reaches the end. So that's a very good, this would be a good pair of sunglasses, blocking or UV sunglasses, assuming that they have UV protection on them. But this is a good example of a good blocking of two polarizers working together. Typically, the higher the angle, the more the blockage you have, or the less intensity you transmit through. Let's see the next problem. This is interesting. It's a very simple one, but I wanted to bring it in case you didn't read a textbook yet about it. So what is Brewster's angle? Brewster's angle is nothing else but the polarizing angle. And the question is, what the heck is polarizing angle? Well, it's an angle that it's an angle of incidence between the normal and between two mediums, right? It's an angle of incidence into one medium at which you will have fully plane polarized light, meaning that most of it will come out, if not 100%, fully, okay? So they ask you, it's almost like total, because it's not internal reflection. Now, I cannot make that comparison. So just complete polarization, I'd say, complete reflection, I would say. Alright, so Brewster angle is defined as what between the two index of refraction of your glass and the air in this case. Yeah, we have both of these, 156 for the glass and 1 is for the air. So that kind of conducts to an angle of 57.3. Now for each, you can have air and water, air and glass, multiple air and plastic, and so on and so forth. So you will find probably a table with all these Brewster's angle, and that's how they calculate what is the best angle for sunglasses, for example, except that's air in air. So they have to have two layers, right? So they have to have polarizers in between. So. Alright, the last problem that we have to deal with is problem 9. So they ask you at what angle you should have the two axes of two Polaroids, which is nothing else but two of these polarizers, to be placed to reduce the intensity of the incident unpolarized to either 1/3 or 1/10. You know, this is the same like problem 7, except they don't give you the angle, they ask you to calculate it. But the relationship in between all of those intensities stays the same. So let's go back there and look at it. So here we have the same thinking. You have unpolarized light coming in, less intensity going out, typically a half, then less intensity going more out of the second one. I tried to change colors here to see that's more light and more light anyways. So I1 is a half of I0. I2 is I1 cosine square. If you plug in I1 with 1/2 I0, you get 1/2 I0 cosine square of theta. So in the first case, they tell you, hey, I2 over I0 is 3. So this is kind of like inverse what we've did in the other problem, where before they ask you a percentage, right? So here will be 1/3, so you just plug in your numbers for it. You get 1/3 must be equal to all of these quantities, right? I2 and I0, simplify I0, and you get 1/3 equals 1/2 cosine squared of theta. It's like a trig equation, essentially. You isolate cosine squared of theta, right? You multiply with 2 on both cases, or on both sides, and then you square root it. Once you square root it, you get theta is inverse cosine of square root of 2/3. Plug in your calculator, and you get about 35 degrees. Now, the second part is 1/10 of an intensity. Same thinking. So in this case, you're going to have 1/10 equals 1/2 cosine squared of theta. You simplify this by 2, and you get cosine of square is equal to square root of 1/5. Hence, theta is inverse of the cosine of square root of 1/5, which gives you 63 degrees. So the higher the theta, the less transmission or more blockage you have. All right? I hope this helps, and we're going to meet tomorrow for questions. I think it's tomorrow. Let's see, Wednesday. Yes, tomorrow at 4 o'clock.